So first things first, I want to thank you guys for coming out tonight, but most importantly, thank you for coming out to our welcome night. What did we all think? We had a good time?
Great
food?
time.
Awesome. All right. So there are going to be other social events that we do throughout the year. And of course, we welcome all of you to come out to those as soon as we announce them. We also do have a general meeting, our next one coming up in 2 weeks from today with Rich Thompson, another fascinating individual who will be, of course, giving more of that SPC perspective. But a very, very interesting presentation nonetheless. So before we hear from Cameron Nixon tonight, just a couple of business items. I already talked about number one, which is our next general meeting. I also want to mention too, and just keep this in the back of your mind, that in October, we will have STEM Fest. And as part of STEM Fest, we will need volunteers. As we get closer to that date, I will be sending out some information for those that are interested. So definitely by next general meeting, if you guys are interested in partaking and being a volunteer for STEM Fest here at NIU, we'll have a sign-up sheet for that and we'll get you more information. It's a great volunteer opportunity to get involved. So if you are interested, keep that in mind and we'll get a sign-up sheet together for our next general meeting. All right. The other business item is over the last few months, our e-board has worked with pretty much a lot of time in developing our brand new constitution. In order for us to ratify this constitution, we not only need approval from the National AMS chapter, the SGA, but also all of you. So far, we've gotten approval from the National AMS chapter, we've gotten approval from SGA, and last but not least, we need approval of a 2/3 majority of the voting members of AMS. So without further ado, I'm going to bring up Lexi, our Vice President of External Affairs. She'll talk a bit about what is in our Constitution.
Hi, I'm Lexi. I just kind of want to give you guys like a brief idea of why I'm the one describing this stuff. I've been voted the most concise talker or speaker for the board, so it's kind of, I'm giving you guys like an overview of the Constitution. What we're going to do thereafter, though, is we're actually going to give you guys a form, and we're going to give you a copy of the Constitution so you can read it through. So I'm kind of just like the gist maker, okay? So my role as the VP of External Affairs basically means that I'm going to be the one talking to those who are outside of like the AMS stuff. So like I'm working on a project with Katie. We're going to go travel to schools outside of NIU to talk about what AMS and meteorology is. But that also means that I talk to SGA. So like, you know, the stuff that makes us an organization, that's kind of like what I do. So because of that, here we go. I'm going to go over the Constitution really fast. So we've got the preamble, basically just says that we are the AMS chapter of NIU. Article 1 just gives us the name of the chapter. And then Article 2 is our mission statement. Now I am going to read that in its entirety just because I feel like the mission statement is kind of important. So it says the Northern Illinois chapter of American Meteorological Society stands as an inclusive and educational environment that promotes collaborative, cooperative, and connectivity within the Department of Earth, Atmosphere, and Environment. This chapter strives to incorporate voluntary service through community-based outreach and networking with persons in and outside of NIU. Members of this chapter are expected to uphold and promote the values of this organization and this university. Article 3 goes into defining members. We have two types of members. It's going to be active versus affiliate. To be an active member, basically you just have to be a full-time student at NIU within the EAE department. That's kind of what we're saying is like, you know, yeah, you're a member. Affiliate basically just says like if you go to NIU, whether that's part-time status or if like you're a grad student, that differentiation is just whether you're undergrad and full-time versus part-time and not undergrad. We have a non-discrimination clause. We don't discriminate. Everybody can come in here. Woo! Guidelines for conduct. So that's going to be one of those things that we added this year. So it's basically just saying as long as you're going to be an upstanding individual, you're going to be part of the club. Like we just don't want to see people acting unprofessional and acting like they're crazy. Like we want to make sure we're promoting, you know, a positive atmosphere, and that comes with presenting yourself in a very professional manner. We go through explaining like what that would mean if you were to say not be so professional in a meeting with other people and just be put together is all we're really trying to say. We don't really want to have to enforce discipline, but we do have outlines in case that were to happen. We do have outlines in case there were to be a need for impeaching any of our executive boards. So like, let's say one of our board members is just not doing their job and they're consistently doing crazy stuff. Well, there's a whole process in how that would go if you needed to impeach someone. Then Article 5 goes through exactly what all of our roles are. Since you've been introduced to us, I'm not going to go ahead and bore you with the logistics of that. Article 6 goes through nominations and elections. we just went through it, so I think you guys have some kind of idea of how that goes. Basically, if you want to run for exec board, you have to declare candidacy 2 weeks prior. And if you are running for president, this is going to be the biggest one. If you're running for president or vice president, we have 2 vice presidents positions now, so this qualifies for both. You have to have taken and passed MET 300. We did this to make sure that those who are at the higher positions of the board do have that level of knowledge of meteorology, considering we are a meteorological society. So we want to make sure that there is that threshold of knowledge that you are crossing. And then to qualify for the exec board period, you have to at least be enrolled in MET 300. Again, this is a meteorological society, but we want to make sure that we're bearing that with it. So just read through it if that's something you're curious about. It goes through how we're going to handle post-election procedures, how the election itself is going to be handled, and then we describe what meetings are going to look like. We do have a clause that has a confidentiality component, and that's going to be applicable to our executive board meetings. If you are planning on running in the future, what that would mean is that executive board meetings are going to have this idea that what happens in those meetings stays in that meetings. What that means is we're not going to have an executive board meeting and then have one person go, oh my gosh, this is what happened, this is what happened. Nah, like we don't want to have that kind of drama. We are adults. So if you want to go ahead and read through that, by all means. Then Article 8 covers finances because money is a thing. And then the last article is 9. That's going to be how we would go about amending this constitution if need be. Again, you are all going to have a way of viewing this constitution in its entirety. We're going to send out a Google form and we're going to get feedback if you guys have any, but please read through it. Again, I'm just the one who does the gist. Do we have any questions for now? Okay, cool. I know that was fast. I'm a very fast talker. I apologize.
Cool. The QR code for the vote is right up there. And just as a preface, I did it really quickly. So the comments, concerns, questions thing is not on the ballot. But if you have any questions, comments, concerns, get a hold of us anyway. Yell at us. Do whatever you have to get that. It's the second QR code. That one right there.
Cool.
Yeah, you can put it up there.
All right. So last chance for questions on that. Any questions related to the Constitution? And again, as Lexi mentioned, and thank you for that, you can go ahead and take an opportunity to really read through it. And if you do have any comments or concerns on it, there will be a tab to be able to read that feedback. All right. Okay, well, without further ado, I know Cameron Nixon has been waiting patiently. He is, of course, a grad student from CMU. He will be giving us a presentation tonight about hodographs, but in particular with hail forecasting. So Cameron, like I said, thank you so much for your time. Thank you for taking to talk to us. And the floor is yours, Matt. Go for it.
Nice. All right. Let me share myself. Sweet. Thank you guys for inviting me. This is really cool. I appreciate it, and I always enjoy the opportunity to chat with people who, like, I know this is cliche, but I was literally just in your shoes just a few years ago, and a lot has changed since then. And I guess I have gone down the research realm, especially research to operations. And so if anyone is kind of aspiring to do that, I always like to kind of speak to those people with these presentations. This is actually, I was telling Brendan, this is something that I have actually thrown together for the NWS, and I've actually given a few WFOs kind of a derivative of this talk. And so the goal here is to kind of make this accessible to all audiences too. And so I think you're going to get a lot out of this, and we're going to we'll tread around the hodographs and not really go into the complex details, because those are all on my website or my YouTube. I know Brendan was talking about that, so I don't want to bore you. I just want to talk about hail. So let's get started. I'll just tell you a little bit about myself and kind of where I'm from, because I am from the magical land of Illinois. I'm actually from Crystal Lake, very close by, so I know my corn and I know my corrupt politics and whatever else you want. I also know my warm fronts. And then I went to Valparaiso University, where I initially wanted to become a weatherman. After watching Tom Skilling my whole life, I'm like, okay, I want to go into TV. Friends like my voice. I'm like, okay, this is an easy choice. But halfway through Valpo, something happened, and I witnessed my first tornado. And this ended up being the Rochelle, Illinois EF4 on April 9th, 2015. And this kind of this threw me for a loop, and it put me into a really big shock. And really, that was the very moment that kind of just got my gears turning nonstop and forever. And this is when I knew I wanted to do research instead. And so that's kind of how my path abruptly changed. I could not stop thinking about tornadoes. I could not stop trying to find the next one. It really is kind of a passion-driven obsession. But that's really how I got here today. So embrace it if that's also you. I went to Texas Tech after that. I don't know what you can see and what you can't with this little floating head here. But this was kind of my heyday, I guess you could say, of storm chasing. I really loved it down here around the dry line, and we got our little daily supercell fest. A lot of dusty, dirty tornadoes too. So I really miss my time at Tech. But then I moved back up here to central Michigan, where it's really cold here. It's really boring, but we also get stuff like the Aurora and Steve here to at least keep me a little bit entertained. So can I minimize this? My goodness, there we go. Okay. And so I told Brendan, if anyone has any burning questions here, you can feel free to kind of just raise your hand. Brendan can take them, and you can interrupt me. I really don't care. That we're here for kind of the conversation and not to just hear me droning for a half hour. So what we really want to talk about today is the problem of hail forecasting. And so if you know anything about severe weather, I know y'all are at a variety of different levels right here. We use skew-ts and hodographs and a lot of the parameters that come from this. And so for instance, this is CAPE, convective available potential energy. This is the area between the parcel profile and the environment. This is how much warmer the parcel is than the surrounding environment. And so big CAPE is often thought of as being important for hail growth, right? Because we need a really big, strong updraft to keep those hailstones aloft. We also look at steep lapse rates. These are the basically how fast, how quickly the temperature in the air cools as you go up. So these steep lapse rates have really been very often cited for being a predictor of severe hail. So if you ever read an SPC discussion, you'll hear them say, okay, we got really steep lapse rates today, so this is probably going to be a hail environment. Low freezing level. A lot of y'all have probably heard that a lower freezing level basically cuts out the time that a hailstone has to melt. So if we have the lower freezing level is, the hailstone's going to have less time to melt and will, I guess, retain more of its mass. So it doesn't melt after it falls out. We also generally want a discrete supercell, right? So we want big curvy hodographs like this, which give a lot of streamwise vorticity. And we won't go into detail about streamwise vorticity here, but we're generally looking for our big humped curved hodographs, what have you, for supercells. And maybe we want a really powerful updraft. Maybe we want a supercell that produces a really strong tornado. All of these things combined could give us a threat for guerrilla hail. But the reality is that this is really what a record hail sounding looks like. And for those of us who have looked into detail about soundings, there's nothing, I guess, particularly sexy about the sounding, right? We got about 7 Celsius per kilometer lapse rate here. We got 2,500 CAPE. Our hodograph looks relatively straight. We got weak lull shear, weak SRH. This is a record hail sounding, and there's nothing, I guess, I would say, particularly interesting about the sounding. Nothing about this makes you want to go, whoa, this is crazy, or like we're in such an extreme environment. This is what we're working with. This is a record hail sounding. So we got to figure out what is in this sounding or elsewhere that actually allows us to get big hail. So the topics we're going to be covering today, and I spent way too much time on this right here. I love this, and you can't tell me otherwise. How does hail grow? What are the ingredients for big hail? And how do hodographs relate to hail, and how do skew-ts relate to hail? And so at the end, we'll kind of mesh both of these together because you really can't look at one thing in isolation. You got to look at both at once. So how does hail grow in the first place? Well, hail starts as these little baby hailstones or little ice pellets that we can call hail embryos. And there is an entire kind of region of the storm dedicated to the production of these embryos. This is called the embryo curtain. And it's this kind of, I guess, finger of reflectivity that kind of wraps around the southern parts of a storm. And it's actually co-located with the flanking line of a storm. So if you know your supercell diagrams, you have your big downdraft right here. You probably have your primary updraft kind of right here, and then you have a flanking line of storms that feeds into that supercell and allows it to sustain itself. And if you've dug deep into radar, you probably know this is a weak echo region or a bounded weak echo region. And this is where the strongest updraft is because it's punching all this clear air northward. Your rain is literally kind of deflected around your updraft as it grows larger. So this is the primary updraft here, and then this is the flanking line. And so initially these stones are born in kind of the outer reaches of the flanking line. Then they kind of go through a little adventure. They get caught in this flanking line, which is kind of full of these individual developing cells, each pulsing up and down. And you can see this this kind of cyclic nature of where this hailstone is. Is it in an updraft? Is it in a dry updraft, a wet updraft, a downdraft? All these things can add layers onto this hailstone, kind of like an onion. And so this is due to its kind of chaotic tumbling nature within the storm. But eventually we're going to get to the tippity top of the primary updraft here, the biggest one. And then it's going to add even more mass to this hailstone. If you look closely, this one in particular, it almost looks like this is made up of a lot of little hailstones. And that's really what can happen because once you kind of freeze together a bunch of little hailstones, it's almost like you're just gluing stone on stone on stone. And then this is how you can really get these larger stones. And ultimately, you're going to follow the ground. Some farmer's going to find it and be famous, like I found him on the first page of Google Images. And now he's on my slide. So what makes larger hail? This is what I have been tasked with this PhD. And what we want to know, or what we do know, are generally more hydrometeors within the storm are better. And by hydrometeors, I mean anything like ice particles, grapple, liquid water, all of these things. All it is mass. We need more mass to kind of combine onto these hailstones and just make them larger. If we don't have mass, if we don't have precip, these stones aren't going to have anything to kind of latch onto, and they're just not going to grow as big. But we need to also, most importantly, spend the most time as we can in this region in the mid-levels of the storm called the hail growth zone. And so what this hail growth zone is if you've heard of the dendritic growth zone, it's kind of the most favorable temperature region for snow. I think it's -12, -18 or something like that. This is a similar idea. This is just where the microphysics are most favorable for the formation of hailstones. And this runs you between -10 to -30 degrees Celsius in the mid-levels. And again, so this is the mid-levels. This is around-ish 6 kilometers, 4 to 8, whatever. Not the upper levels of the storm. This is the mid-levels. And we also want to spend more time in this embryo curtain, which, like I said, is the flanking line of a storm. This is what it would look like if you're chasing. This is what it looks like on kind of a 3D volume rendering. You can see that little curly cue of these updrafts as they're sheared apart. And this I guess, conveyor belt of developing hail embryos eventually falls into the main downdraft here. And so what we know about hydrometeors is that wider updrafts yield more hydrometeors and potential hail embryos. So when we're comparing something like maybe like a skinny LP or maybe like a mini supercell, like we often get up here in the Midwest in the summertime, these updrafts just really don't have enough mass, I guess, to produce these really big stones. Whereas these really big, girthy kind of updrafts have enough mass to contribute to hailstones. And we also know that more precipitation also, again, this is another hydrometeor, another thing that can kind of glue onto these hailstones in their little adventure. Having more precip next to the updraft is often a bonus. You don't have to have too much, but this is also one of the reasons why a lot of people associate big hailstorms with HP storms, potentially. And so what we're looking for then, this is the tricky, complicated part that I will try to kind of just gloss over in a friendly fashion. But what we're looking for within these storms are favorable pathways that these hailstones take in order to allow them more residence time within the storm. So for example, we want a stone that, as we talked about earlier, it starts in the embryo curtain, the flanking line, and continues, stays within this favorable chain of updrafts, and then falls down. Because what happens then, if you look at it in a vertical sense, this hailstone is going to spend a lot of time within the confines of this temperature zone, right? It goes up, it doesn't go too high, it goes back down into that hill growth zone, goes back up, it's still in that hill growth zone, still in that hill growth zone, still in that hill growth zone, and then finally it falls back to the ground. So we've just maximized our time in the mid levels of the atmosphere if we start off in kind of a relatively weak updraft. And kind of a visual of this would be this beautiful storm here, whereas you start in maybe one of these developing updrafts, we're continued, maybe you fall out a little bit, maybe you go back up into this main updraft, and then you fall back down again. These hailstones can do some really random things, and this is kind of how they grow and how you can prolong the time that these things have in the updraft. What we don't want is pathways that give you less residence time within the storm. So in this case, maybe we eject a hailstone out way early before we have time to spend in that embryo curtain. Maybe we start this hail embryo in the center of the primary updraft here. Then what's going to happen is this updraft is just going to loft this straight through the hill growth zone and out into the anvil. That's no good. We've only spent probably 30 seconds in the favorable part of the storm, and this is not going to yield you big hail. And this is kind of backwards because a lot of people think that your most strong, your most intense updrafts are what are needed to keep this hailstone aloft. But these can actually be a little bit detrimental because they don't allow this hailstone enough time to be where it needs to be to grow. Any kind of particle that originates here near the tornado is really just going to end up as some anvil debris and really not grow big enough to be noticeable. So the problem then that I'm tasked with is figuring out how you get these complex pathways here with the environmental variables, and it's definitely as hard as it sounds. And so a lot of hail forecasting has been a very complex problem that we're trying to boil down into really simplistic ways. Sometimes it works, sometimes it doesn't. And there's two main controls here that how the environment can impact these storms. One of them is through widening the updrafts, and another one is through providing more residence time within these updrafts. And we have to come up with ways from the shear profile and the thermodynamic profile to predict this. So how we use the hodograph then, and so for those uninitiated, this is a hodograph, and we have our wind with height here. So at the ground, we have a wind blowing from the east, blowing to the west here at about 10 knots. You see that 10 knot range ring. Up at about 2 kilometers, we have a south-southwest wind blowing at about 25 knots. And then you rapidly increase in strength, and you're still blowing from the southwest. And what really matters with these hodographs then is how the storm is interacting with it. Here's our right mover storm here. We're going to assume that that's our storm motion. And so this is almost like if you were to be driving down a highway at 60 miles per hour, the day it might be calm, there might not be any wind outside, But if you're cruising 60 miles per hour, you're going to feel a lot of wind at your face. And so that's exactly what we're looking at here is the inflow to a storm depending on how it's moving. And so in this case, the wind this day was only about 10 knots at the surface, but a right mover was feeling 40 knots. And so what this does is the stronger storm relative inflow at the face of these storms can actually provide more mass into the supercell. And for those of you on Twitter, this has actually been a topic that some people have been throwing around and trying to incorporate in cool ways in Hodographs, because it is really cool, this idea of mass flux. And this was really started by John Peters in a lot of his recent work. And so what we're finding is that these environments with stronger storm relative inflow can sustain larger supercells, like this big chonky thing that approached Hondo, Texas, and produced the state record hail. And so we're really looking for environments with strong storm relative inflow to give us bigger hail. Whereas if you're from the Midwest, you are probably intimately familiar with this photograph here, which features very weak storm relative inflow. In this case, we have less than 20 knots or so. And so when you have inflow this weak from the environment, you might only sustain these mini supercells. And this is how most of our classic Midwest MCV or otherwise kind of warm season mini supercells arise from photographs like this. And as we talked about, these small supercells just really can't get it done in terms of big hail production. And lo and behold, this was a study on gargantuan hail, which I think they said was greater than 6 inches, and small hail. And one of the biggest differences was not in photograph shape, but how the storm interacted with that photograph, and the storm relative inflow that these storms felt from these environments. So the residence time then is a whole nother problem. And the residence time, we can kind of connect this back to our updraft width problem, because the bigger and wider your updrafts are, naturally the more kind of real estate a hailstone has to traverse through the storm. So wider updrafts are typically better for residence time here. But we also have some issues. Residence time can be disrupted by low-level shear. And this is probably one of the biggest findings in the last decade or so. And this came from this Denison Cumgen study, and what was doubled down by this recent Cumgen study too. And what we're finding is, in a very simplistic sense, stronger wind shear is going to create these pathways that really quickly eject these hailstones out of the embryo curtain, right? And that's no good for them to be able to grow. And this process is also, very interestingly, disrupted by intense mesocyclones. Because if you were to release a bunch of hailstones in an intense meso, what is a meso but a really intense updraft too? So you're just going to immediately go through that meso and up into the top of the storm. And this is actually something that, if you follow the IBHS hail study, if you don't, I recommend it. This is a group that's going around and collecting hailstones and trying to look at, okay, what were the conditions and what was the storm like when this was produced? And they actually noticed multiple times, even after this, that once the updraft of the storm went tornadic, hail production kind of decreased or even ceased. And this is something that I'm finding in my research too. So there's this really cool balance between tornado and hail. And this is only the beginning. I'm going to talk a lot about that throughout the rest of this talk. But so by and large then, what we're looking for our hail photographs are weak low-level shear, generally, and some cloud layer shear. And for any severe weather nuts here, this is a very boring photograph. there's nothing special about this. And of course, this is in the average sense, right? There's a lot of variability that we got to look at. But on average, your photographs of large hail are very boring. And what has really haunted me throughout my research is that, unfortunately for me, the photograph cannot predict hail size alone. And so we end up with you can compare your small hail hodograph here with your giant hail hodograph here. And in a mean sense, if you're trying to predict hail size with just this, good luck, right? You can't. They're all the same. And so that's been a huge issue for me. But we have seen some clues in more simulation studies that do show on a case-by-case basis, stronger deep layer shear is actually associated with greater hail production, especially hail mass. And your very own Dr. Gensini has also found this in his work using machine learning. Essentially seeing that mid-level shear signals do actually correlate a little bit with hail size. And so this is important because this is something that hasn't fallen out of the mean kind of research. But what we do know is that the hodographs of hail are very different from those of tornadoes, because the strong low-level shear is quite typically detrimental for the hail process. So you get hodographs like this, these really are not very good for hail at all, but these ones are. So this is what we do know and can kind of grab onto. So kind of in a very general sense, and I'm going to talk about some caveats and when this doesn't work. You get kind of a spectrum of environments that might, on one end, have weak low-level shear and be conducive for hail and really not tornadoes, because tornadoes love that low-level shear, that streamwise vorticity, those large curved hodographs. So this is a hail hodograph, and this hodograph on the right here has much too much shear for hail production. So we're really just a tornadic hodograph without the hail. And then somewhere in between, you could probably get both hazards. And so what we've been working on the past couple of years then is trying to figure out how many different ways we can get hail. What is the variance of our hodograph shapes that lead to big hail? And if you know how to quantify, right, veering is winds constantly turning with height, backing aloft. A lot of people think this is bad for severe weather, but it's not. You can have all sorts of shapes here that do lead to big hail. And throughout the rest of this talk, I'm going to be mentioning big or large hail. That's just me saying 2 inches and greater. The kind of stuff that can really hurt you if it fell on you. And so this is what we're trying to figure out. Why is there so much variation here? Why can I get the same hailstone with this dinky little hodograph here as I can with this really huge long hodograph here, right? All of these are doing the same thing. And what we've seen is that in a mean sense, again, right, the hodograph is not changing, but the skew-t is. We're getting more buoyancy. But this doesn't help us. This is one little parameter here, right? CAPE is increasing as we get larger hail. Nice. How is that supposed to help me? It doesn't. And recently studies have actually came out that there might be actually a Goldilocks zone in the amount of CAPE necessary for hail, and that too much CAPE might actually be too much CAPE, and that we might need something in kind of the mid 2500-ish range to be best at producing severe hail. Because they're actually finding that this impacts the residence time within the storm as well. And so there's all these complications here. But some of the more, I guess, widely used parameters today include lapse rates, right? We talked about how the rate of temperature decrease with height is very often cited as favorable for severe hail. But to make things complicated, people are finding that these lapse rates are really kind of specific to the US and similar countries, and they don't work in other countries such as Europe, where a lot of their hailstorms occur with really weak lapse rates. And so I'm starting to wonder if lapse rates are not really a necessary ingredient, but maybe an indicator that yes, this is a plains environment and everything that goes along with it, the CAPE profile, the moisture. There's some secrets hidden in lapse rates that we really haven't figured out yet. But by and large, it's kind of mostly just an indicator or a suggestion that this is potentially a hail environment. Freezing level, unfortunately, has not been found, at least recently, to affect hail size either. So we know that it works to some extent where like if we have a higher freezing level, you're gonna have more time to melt your hailstone before it reaches the ground. But this really doesn't have any skill in predicting hail size, which is really contrary to what a lot of people think today. So what we're trying to figure out then is how can we use the hodograph and the skew-t in full and not just these single parameters here, to kind of ascertain a balance and try to figure out what impacts what and how. And so what I did for most of my research, and for those of you going into research, this is kind of a glimpse into your future. And what we're doing is we're using machine learning. And I'm one of those people who I'm very much a purist. I don't like letting machines do things for me. I want that control. I want to do it myself. And I had to succumb for this and just kind of let the computer do its magic, because this actually gave us some really cool results. And I thank my advisor for pushing me to do a little bit more complicated stuff that I really wasn't comfortable with. And so what we did for this is we used a self-organizing map. And what this is, it's a kind of machine learning algorithm that takes in a lot of data. So in this case, we basically fed it 7,000 plus hodographs, and it's going to kind of organize these into a few clusters. So it's going to learn and say, okay, hey, these 3 hodographs look pretty alike. So we're going to assign this to this cluster. And in the end, we're going to have a grouping of the most common clusters, and this is going to be one of them. And this is going to be really important because then what this is going to give us is kind of like the X number of most common ways we could get hail. And so this is what it came up with. And this, I really didn't like at first because there's so many different shapes here, right? You don't even have to know anything about hodographs to tell me that these all look different. We have small hodographs, we have big hodographs, we have lots of low-level shear, which I already told you was a bad thing. And we also have weak low-level shear. There's so many different ways to get hail. And so, you know, like I'm slamming my fist on the table. I'm like, is every hodograph a hail hodograph? And I need to figure out what's the rub here? Like what's why? So we needed to introduce the skew-t here. And so what we did for this first study is we fed this machine learning algorithm only the hodographs, right? We're only going to give it the context of the hodographs, not the skew-ts. But afterward, we can have the computer say, okay, hey, these are the hodographs we have, but I was able to fish back out the skew-t that was associated with each one. So if that makes any sense, we gave the computer the hodographs, they're going to spit out the skew-t that was associated with that hodograph. And so what we can see here is that if we kind of hone in on maybe these reds versus these blues here, as we change your hodograph shape, the skew-ts are actually a little bit different. Where we have these smaller hodographs, especially with weaker low-level shear, we have generally larger cape. When we have these much longer hodographs, maybe with stronger low-level shear, we have a little bit more marginal thermodynamic environments, right? We have a lot of sin here. We have a little capping inversion here. Maybe we have another cap and some dry air here. Maybe we just generally have weaker cape than the rest of these. So this is where the gears started turning and saying, hey, there's something here. There's some relationship. There's some cape shear balance. And already this is kind of the opposite of what you're used to thinking, because as we increase shear, our skew-t is getting a little bit more marginal. So why is this? When we trained the self-organizing map then, and we said, hey, all that you can process are these skew-ts. We're only giving it these skew-ts to look at. And then it's going to spit back out the hodographs associated with each one. The hodographs are all the same. And so what this means is that the skew-t is not changing the hodograph. So you can have big cape and a lot of dry air. You can have really skinny cape. You can have more big cape. You can have any kind of cape profile you want. You can be elevated. But the hodograph doesn't change. You don't need a specific hodograph for a specific skew-t. You need a specific skew-t for a specific hodograph, but you don't need the reverse. So when we fed it only skew-ts with weak cape, you can see this even more clearly. These photographs are just as different and kind of diverse as they were in the first sample. Cape is weak, photographs can be just about anything they want. But when we have strong shear, our cape generally has to be weak across the board. We must have inversions, we must have elevated storms. We must have, when we have a little bit more cape here, we're really dry, which actually decreases the effective cape we have. So all of these have generally weak cape when you have strong shear. So this is telling us that a storm must be in an environment with weak cape if we're in strong shear, which again is really backwards, because if you're used to tornado forecasting, you know that if there's weak cape, we need strong shear to kind of compensate for that and create stronger storms. But in this case, if we have strong shear, we need weaker cape to compensate for this. And likewise, if we look at just our low-level shear, and then we get these big curved hodographs, like I already told you, weren't really good for hail production, you see something really interesting. There's a huge capping inversion in all of these, and some of these are elevated storm scenarios that are kind of elevated above this shear. And so what we're seeing here is that if we have strong low-level shear, we really need our storm to just not feel it. We need as much sin and inhibition as possible to kind of overcome the strong shear. We want the storm to be as free of shear as physically possible in these low levels. And so we're going to do that by making it really hard to ingest that shear, by giving a huge cap or elsewhere. So what does this mean, right? This is all really complicated. So let's boil it down into just a couple main themes here. This cape shear balance is only one-sided. Large hail is possible with a variety of skew-ts, regardless of the hodograph. But large hail is possible with a given hodograph depending on the skew-t. And so specifically, if cape becomes stronger, shear can be weak or strong or whatever. It doesn't matter. But if shear becomes stronger, cape must be weaker, and sin must become stronger in these cases. And so this is a really cool kind of addendum to our current forecasting methodology, is because we really before this have not been able to know how these two interact. And so in a special case with an elevated storm, kind of what we think is happening is you have your effective inflow layer. This is essentially where the storm is pulling its air from. And we can take a tornadic environment, and if you become an elevated storm and you're only pulling in this air above the low levels, you're only going to have weak shear, and this is going to be a good hail environment. But one of the kind of confounding factors to all of this, what I've just told you about the environment, is that a storm's structure and morphology and your storm mode can heavily impact its behavior. So we know that supercells account for the vast majority of severe hail, right? MCSs don't. This is really the main way we get hail. But these interactions, again, it's like a confounding variable. This was our Hondo, Texas record hailstorm. And you can see how many cells it kind of inhaled before it produced the main result. And this is something that we just can't tell from the environment. And so this is, I think, going to be a pretty important kind of avenue of research as we go forward, that we really need to look into the intricacies of storm mode. Because what really matters is the kind of the finished product, storm structure. How it got there is kind of irrelevant. So for a little review, what we talked about is that weaker inflow layer shear is usually necessary for big hail because this helps residence time. Larger supercells can produce bigger hail because there's more mass flux into the storm. It grows bigger. It has more embryos and hydrometeors. And then the storm is happy and can produce bigger hail. More CAPE is good, but too much CAPE is too much. We generally don't want huge CAPE profiles like this, despite what a lot of people do think. And for stronger shear, even though stronger shear has been found to be better for hail, as we get stronger, we really need CAPE to be a little bit weaker to compensate. And especially for low-level shear, we really want some thick sin here, some convective inhibition, and something in the environment that's really prohibiting that storm from feeling that shear. But for any kind of CAPE, weaker, stronger, what have you, shear could be just about anything. So this CAPE shear balance really is one-sided. The hodograph cannot predict hail size alone. So you can't tell me, hey, Cameron, we have a really huge hodograph today, so we're going to get big hail. You can't actually tell me that. Generally, in a mean sense, hodographs are not a very reliable way to predict hail size, but our CAPE is. And last but not least, storm mode matters, perhaps even more than anything else. And this is something that we really need to look into further. So I'll leave you with some sites you could look at for hodographs to learn more about them and how they work operationally. This is the SPC mesoscale analysis site, and you can see they actually have effective info layer here, so you could play with that. The College of DuPage site has their storm relative hodographs, which I have a soft spot for because this will actually tell you the storm relative winds from these hodographs. And then the Pivotal Weather site, honestly, this is probably my favorite just because they have all the models, all the hodographs. This is a really cool tool to use on severe weather days. Another site, if you have not bookmarked this one already, you should. This is autumnsky.us/vad. This is Tim Sapini's hodograph plotter, and you can take real observations from radars and kind of dissect the vertical wind profile from their scans here. And so you can get, this was in proximity to a really long-lived tornado in Alabama. And you can compare this to the ustornadoes.com/case archive site, where we actually have a lot of photographs of past events. And I'm going to actually try to put more from historical events too onto here. So maybe the Palm Sunday event or the super outbreak. And so you'll be able to kind of compare the latest photographs with stuff that already happened and see if there's any similarities. So with that, I am done. I have rambled long enough, and I want any questions that you guys have.
Questions do we have? Yeah, go ahead.
So elevated thunderstorms are high base thunderstorms, right?
No, they are not. And so that's one of the most common misnomers. Let's see if I could find a slide that was good for this. Perhaps this one. Zoom in on this. So high-based storms, and I don't like this because the more I think about it, high base, right? We're talking about an effective info layer base. So I get where the confusion is coming from. Like I've heard this so many times. And what we're looking at for a high base storm is we need our LCL to be high, right? I guess high base is visually our cloud base is high. And whereas for an elevated storm, you physically, you're ingesting parcels from a loft, usually above kind of a stable layer. Your air below is too cold for that storm to ingest. So you're ingesting parcels aloft. And this is a really tricky thing to get your head around. But therein lies the difference between high base and elevated. They are different.
Thank you.
Yeah.
Other questions?
Yeah, so my name's Ethan, by the way.
Hello.
There's supercells out there that produce, inches and inches of accumulating small hail. And then there's supercells out there that just produce, a bunch of larger hailstones, but not necessarily inches of accumulating hailstones. Is there a good way to kind of forecast one versus the other?
I would read this I don't have, it is, I think it's a 2019 or a 2020 paper by Matt Cumgen, Splash. I forget the acronym, but something accumulations of large hail, or accumulations of small hail, sorry. And so I personally, in my opinion, I think we got a bit of work to do on that. We did find that storm relative inflow difference, but I think there's a lot more to come from that. But that's a cool paper to read.
Thank you.
Yeah.
I was going to add to sort of the thing that I've been wondering, and I think you and I talked about this before your presentation today. You know, a lot of your research has been obviously focused on the hodograph. What was your inspiration behind that, or was there a particular event or something along the line of your academic career that clicked with you?
That is a really good question. So if anyone has seen the deviant tornado motion stuff, I was at Texas Tech, and I was, full disclosure, I was doing a project that I just really didn't enjoy as much as this. And I was looking for basically anything to keep me occupied that brought me back to severe weather and dynamics and stuff. And NWS Lubbock was giving a talk on predicting deviant tornadoes using the hodograph. And I'm like, okay, this is kind of cool. And I think that was the first moment that my mind kind of just started racing and never stopped. So I think that was it. I'm really good at pattern recognition, and I'll do that in my spare time. And like, I think that was the thing that got me into hodographs.
Anybody else? Questions?
Yeah, I have a question.
Go for it.
My name's Kelvin.
Yeah.
How important are some of these field studies regarding hail in some of this research that's coming along, particularly yours, if at all?
I would say, I mean, like, the correct answer would be that they're very important to me personally. But in my 3 years here, not as much so important. We're trying to use really large data sets so that we can say with more certainty, okay, this is what happens. But those field studies are, in my opinion, just as important, if not more important, than those that go into tornadoes, because we're really decades behind on hail research, and really anything that we could find on these campaigns is cool. And they've already found some really cool stuff. So again, please follow, if you don't, IBHS hail study, because there's some cool things that go on in there.
Anybody else? Second questions?
And I will happily answer grad school questions, because I know it's a whole different world, and it's made me a different person for better, for worse. And anything you have either now or just shoot me a message somewhere, I'd be happy to answer that.
Well, I guess for a final question then, what would be your advice for those that are looking to go into grad school, interested in grad school? What would be kind of your...
Yeah, low-hanging fruit, I like it. My number one biggest advice, you heard me touch upon this, but my time at Texas Tech, I accepted a project that I was not into as much as I should have been. And I knew going into this that, like, okay, I don't really like this project, but there's tornadoes. And that was my logic. There's tornadoes, all my friends were there, it was going to be a fun time. And I assure you, it wasn't as fun as I thought it'd be. So that's my stern, kind of harsh advice, is that be sure not to settle when you're picking a project. Make sure you choose something that you are truly passionate about. Otherwise, it's going to be a long 2 years. And when it's, like, people stay in grad school forever because they truly like what they're doing. And I found my project here, and I'm really super passionate about this. And this is what I've been missing. So I guess you do as I say, not what I do.
Gotcha. Well said. Last chance for questions. Yes. Yeah, go ahead.
Hey, I'm Chris. And my question, what about upper level assured, because there's this philosophy that like you need strong upper level assured to like evacuate the hydrometers that are up high. So how does this apply to hail production?
Good question. I don't think I know enough to answer that, to be completely honest. I do see, in our results at least, there are a variety of different storm relative wind profiles, right? You could have really strong ventilation, you could have really weak ventilation, but that might be something that goes in tandem with CAPE that we're just not looking at. Good question.
Yeah, Landon, go ahead.
All right, I'm Landon, and my question is, have you found anything interesting regarding like mid or upper level dry air and its impacts on hail size or hail production?
That's also a good question. I think what's interesting about these dry air cases, let me find an even better one, perhaps this, is that I don't think we fully know. I think there's something there. I think there is something there with how much, because essentially when we can have more moisture, right? We can have higher dew points, which is going to give us a higher mixing ratio and more water. But if that's dry, I tend to think that a lot of that more of that water is going to go toward hail than it goes toward rain. So I think that's why we're seeing that we generally have high dew points, but also dry air, is that it's more efficient. All the water goes toward hail and not toward rain. But this might just be a crazy idea that, I don't think anyone has really looked at or talked about yet, and it's microphysics, so it's beyond my understanding. But I think there's something there, and I think you're onto something.
Last second questions. All right, we'll give it up for Cameron Nixon, everybody.
Thank you guys so much.
Thank you so much for, of course, stopping by and taking time out of your day to present, as I said. And of course,
Yeah, for sure.
A last second question. Is there any contact info for people that want to reach out to you and connect with you?
Good question. I used to have a contact slide, so that might have been good for this, but we can just do cameron.nixon@cmitch.edu. And if you search me on Twitter, you will find me.
Awesome. And of course, that's where you're known as well on Twitter. So I think a lot of folks reference Twitter for sure.
For better or for worse.
Well, that's going to conclude our meeting, guys. Thank you so much for coming out tonight. If you haven't, by the way, followed our socials, we do have a website, niuams.org, where you can find our Instagram, our Twitter, Facebook, all that good stuff, and our meeting schedule, as well as even some climate reports that we keep track of with our weather station back by the football stadium. Thank you, Eric, for doing that. And that is it. We'll see y'all in 2 weeks for our next meeting with Rich Thompson. So that's been out.
Thank you, guys.
Don't forget to scan the Constitution
Appreciate it.
form. Everybody can do it, everybody.
One on the left.
Yeah, the one on the left.
Thank you, Eric.
Thanks, guys.